This is 3.12 Photoelectric Effect. Our outcome is I can explain the properties of an absorbed or emitted photon in relationship to an electron transition in an atom or molecule. So, the photoelectric effect is the emission of electrons when electromagnetic radiation, such as light, hits a material. Those electrons will be called photoelectrons. So when a photon is absorbed or emitted by an atom or molecule, the energy of that species is either increased or decreased by equal to the amount equal to the energy of the photon. So the wavelength of a photon is related to its frequency and the speed of light. This is describing the wave-like nature of light. And here we can also relate it to its frequency. So particle-like, we can calculate the energy of a photon. So first thing you have here is a video to watch. And then we have a sample of hydrogen here that we're going to discuss. So I actually had a mistake in my diagram. This is how the diagram is supposed to be. So if your answers are a little bit different than mine, that's going to be why. So which electron represents the largest amount of energy? That's going to be the one at 410 nanometers, which is traveling from 6 to 2. So this purple photon is going to be shorter wavelength, thus higher frequency, so higher in energy. To calculate the energy that is released by the electron as it relaxes from 5 to 2, so I'm going to use its wavelength to determine its energy. So first I converted my wavelength into meters. We were given nanometers. And then I just substituted into HF. This is what F is equal to. So I just plugged that in and solved here. And this is the amount of energy per photon. So this gives me the energy of that transition. Here we have a PES. So remember that in PES, we're looking at the arrangement of electrons in an atom. So it's photoelectron spectroscopy. And the more strongly attracted the electron is to the nucleus, the higher the binding energy is going to be. So we get these specific binding energies that correspond to the energy levels in the electron configuration. In this case, we end up with calcium. So we want to calculate the wavelength in meters of electromagnetic radiation needed to remove an electron from the valence shell of an atom of the element. So the valence 4s2 electrons have the lowest binding energy per electron. This is because they're farthest from the nucleus. So we just got to figure out what wavelength should a photon have in order to possess that amount of energy. So first I solve for my frequency necessary for that energy, and then I converted using my other equation. I just solved for wavelength by dividing the speed of light by the frequency of the photon, and I get 203 nanometers. In the upper atmosphere, ozone is decomposed. So that's because it's absorbing some very high energy ultraviolet radiation from the sun. So I need to calculate the energy of the photon to have this particular frequency. So I'm just going to use my E equals HF, plug in and solve here, and I get this amount of joules. So that's per one single photon. What if I had a mole of photons? So I just need to multiply joules per photon by photons per mole, so I get joules per mole. So does this photon have the required energy? Yes, the photon energy is higher than the binding energy of the electron. So if that photon collides with a 4s2 electron, it will remove it from the atom. It will ionize it. So better for this to happen to ozone than for it to happen in, say, the DNA in your cells. So relationship between energy, wavelength, and frequency. Short wavelength is high frequency, which is high energy. How does this relate to the flame test? So in the flame test, what you're actually observing are those transitions between those energy levels. So that's what the photoelectric effect is showing us. That energy being re-emitted by those electrons as they move down energy levels.